Hello. So in this video, we're going to look at Haberman's section 3.3. And kind of the whole point of the section is looking at properties of even and kind of odd parts of functions and kind of what those pieces look like for Fourier series. And so kind of there's a definition in a bit, but just as a refresher. So for an even function, these are functions that satisfy f of minus x is equal to f of x. So like cosine, it's an even function. Whereas for an odd function, these are functions that satisfy f of minus x is equal to minus f of x. Okay. Right, and so the reason that we're talking about these is because, right, Fourier series are composed of just even and odd functions. And so kind of one of the other goals of this section is to discuss aspects of kind of extensions of functions, right? And so one sort of extension that we've already seen, already worked with, are these periodic extensions, right? Where you sketch your function and then you copy that sketch, you know, plus L, plus L, plus L, and then minus L, minus L, minus L, whatever. And so kind of the question is, well, right, generally we like working with, kind of for these Fourier series, we like working with the interval negative L to L. So the question is, well, what if we're just given information about the function on half of the interval? So like 0 to L. How do we extend it? What are other ways of working with it, et cetera? Okay. Cool. So kind of as I had written above, right, what is an even function? Well, it satisfies this equality or this property. What is an odd function? It satisfies this property. Okay, and so as we saw, right, sine and cosine are examples of odd and even functions respectively. So kind of an interesting general fact about, right, at least, well, real valued functions is kind of the following. So no matter what function you take, you can write it as a sum of an even function and an odd function, which, you know, when you hear that, you might think it's kind of amazing, or okay, I don't know what you're thinking. But for me, kind of when I first heard this, I was like, oh, wow, it's like super cool. It doesn't matter what the function is. We can break it into its even part and its odd part, no matter how funky the function is. And then you kind of actually get into the proof of it, and you're like, oh, well, that makes complete sense. But kind of this is a general fact that we'll work with. And we've already kind of seen this, right? Because we've expressed a function kind of in terms of its Fourier series, right? And its Fourier series consists of an even part, right, the cosine series, as well as the odd part, the sine series. Okay? But in general, this is true. Any function can be written as a sum of an even and an odd function. And the proof really isn't that bad. So no matter what function you take, f of x, what we're going to do is we're going to write it in this way, okay? So in here, you can think of this as adding 0, right? Right, f of minus x minus f of minus x. This is the same as that, so they cancel. Otherwise, we have an f of x plus f of x. That's 2 f of x. So we divide by 2, and we end up with f. Okay. But the point is, what is written here is exactly the same as what is written here. Okay. Okay, and so then what we're going to do is we're going to kind of reorganize and especially pick out 2 of these pieces. And so the pieces that we're going to pick out are this sum, and then this plus that. Okay. So writing that down here, so just taking all of this, we get this. Taking this difference and kind of, right, bringing it out on its own, we get that. Okay, so this whole expression is still equal to f of x. And what we're going to do is we're going to call this kind of the even part and this the odd part. Okay, so we're going to write that as f sub e, right? So f for the function, sub e for even, and then the argument x, as well as f sub o for the odd part. Okay. So in this way, right, we've written f of x as a sum of an even function and an odd function. And so kind of the remaining verification is that, well, indeed, this is an even function and this is an odd function, okay? But we can check that, right? So if we consider the even part and we plug in negative x, right? For this to be an even function, we want this to equal f sub e of x, right? F of negative whatever is equal to f of whatever, just like cosine. So what we can do is we can, well, take the definition, right, how we defined f sub e, and just plug in negative x there and there. Okay, so negative x there, negative x there. That negative is going to cancel. So we're just going to get f of x plus f of negative x. Okay. All that divided by 2, which is, right, how we defined. I can scroll out a little. This is exactly how we defined f sub e of x. Okay. So what we're calling the even part is, in fact, an even function. And you can go through the same steps and show that, well, it's the same for the odd part, right? This right here is an odd function. Okay. So as I mentioned, right, we've seen examples of this sort of decomposition before, where we've taken our Fourier series, okay, and we've written it as, right, a constant term, which is even, plus a bunch of even functions. So this whole piece over here, that's going to be an even function, right? Likewise, if we just take a bunch of sine functions, add them together, that's going to be our odd piece. Okay. And so kind of one other point I want to highlight is, right, generally when we work with these Fourier series, we work with a period of 2L, right? And so kind of the coordinates will go from negative L to L, right, the total length of the interval is 2L, okay? And similar with, right, sine and cosine, generally we like to think of those functions as having a period of 2 pi, right? So L is equal to pi. Yeah, but anyway, so generally we work with, right, when we kind of take this Fourier decomposition, we have a function from negative L to L, or length 2L. And kind of that's where this n pi over L comes from, but kind of this is a geometry that we like working with. So one question is, right, and this is something that appeared earlier in the course when we were given, a PDE on the interval 0 to L, and we said, okay, let's solve this. And then we got sines and cosines depending on the boundary conditions. But in general, if you want to decompose a function into its Fourier series, but you're only given information about the function from 0 to L, the question is, well, how do we kind of translate it into the framework that we're comfortable with, right, for a function from negative L to L? Okay. And so, well, the answer is, well, we extend it. We extend the function in some way so that it takes values from negative L to L, and then we go through the usual pipeline of, right, computing these Fourier coefficients and kind of going from there. Okay. And so, right, well, how do we extend it? Okay. Generally, we have 2 choices, and kind of these are natural choices. And the language that the book uses really emphasize, or how to say this? I'll comment on the language that the book uses, but when they say, like, compute a sine series or compute a cosine series, implicitly what they're doing is they're saying, use one of these extensions, compute the Fourier series, and then go from there. And that's something that I'll highlight here in a little bit. But generally, we have 2 choices. We can take an even extension, or we can take an odd extension, right? And so kind of the thing to keep in mind is, right, so this even extension, right, this, we want our function to satisfy minus f of x. This, we want to satisfy f of minus x is equal to minus f of x. Okay. And so, right, this negative sign is coming out because, we have our function defined from 0 to L, and we would like to define it from negative L to 0. And so either of these two ways are how we're going to say, well, if X is a positive value, putting a negative, it's going to be a negative X. And so we're saying, well, what is the value of F kind of over here? It's going to be, so for an even extension, that should not be there. But anyways, we're saying, okay, well, what is the value of F over here? That's just going to be something related to the value of F. Okay. And we'll see examples of this here in a second. But we have generally two choices that fit really well with this Fourier or this, Fourier series framework. Yeah, okay. So here we're given a function, f of x, and kind of our domain of interest, we're starting with 0 to L. Okay. So the question is, what are the even and odd extensions of f of x equals x to the interval negative L to L? So for the odd extension, right, sort of what I wrote above was, well, we're going to define let me clean this up. So let me take this minus sign, move it over here. So for the odd extension, what we're going to do is say, well, if, hold on. Okay, I take that back. As I have it written, this is fine. So if z is a negative number, right? If z is some number between negative L and 0, what we're going to do is we're going to say, well, what is the function value for one of these values of z? Okay, take minus z. This, like this. So minus z is between 0 and L. This is where our function is defined, so we know what these values look like. And then we're going to just take minus that value. Okay. So what does that look like in practice? Well, here's a sketch, right? So 0 to L, here's where kind of we're defining our function. This is f of x. Okay. So if we want to know what the function looks like over here, okay, what we're going to do is we're going to take minus z. Okay, so if we're here, it's going to look like that. We're going to take f of z. So that's going to be kind of that value right there. And then we're going to take minus this value. So it's going to be something like down there. Okay, and we're going to draw that right there. Do orange. So I'll write f of z is going to look like that. Okay, so we're extending the function right from 0 to L to negative L 0 so that everywhere here it is an odd function. Okay. And so kind of in this case, this function is a little, I guess, so in this case, we can write, right, well, what is f of x? This just becomes x on the entire interval negative L to L. Okay, so nothing too out there, but the point is we started with information here and we wanted to extend it to information over there. Okay. So what about the even extension? Well, here we're going to define f of, so for z in this range, this interval, what is the value of f going to be? Well, it's just going to be the value of f kind of on the other side. Right, so I'll call that f of z. So what does that look like as a sketch? So if we take a value over here, right, so this is like negative L over 2. Look at the corresponding value over here, L over 2. Look at the function value for f. Okay. Take that value and put it above that thing. Okay. So in general, what do we get? That's going to be the even extension of f to the interval negative L to L. And so in this case, we can write, so f of x turns out to be absolute value of x on negative L in this case. But again, the point is, starting with information over here, we're using it to define the function over there in one of two ways. Cool. So if we then want the Fourier series, well, we've already kind of looked at that process, right? Sketch the function in one of these, in the interval negative L to L, and then take its periodic extension. Okay. So here, the function, so for the odd extension, right, this turned out to be f of x equals x on negative L to L. Okay. So then for the periodic extension, we're going to get something like that. Likewise, for the even extension, here it looks something like this, where f of x was absolute value of x. Okay. So here, if we want to take the periodic extension, we'll take the same profile and then copy it over like that. Okay. So technically, there's something that's missing from the Fourier, or this kind of periodic extension, or in a sense, sketching the Fourier series for the odd extension up here, right? The question is, what happens at the points of discontinuity? Okay. So in the case of Fourier series, kind of this theorem about convergence says, well, what happens when you have a point of discontinuity? The value of the Fourier series is going to be the average of the two. And so that's what that X is marking. But you know, it's not an issue for the even extension because it is continuous. Okay. So another example, we're given this function cosine of n pi over Lx. And so maybe here we'll think of as n is equal to, let's go with 1. Yeah. You can sketch the thing for a different n, but we're going to focus on n equals 1. So we're defining this function cosine of n pi over Lx on this interval 0 to L. The question is, what are its even and odd extensions? So again, for the odd extension, we're going to define it for negative z. What is the function value? Well, look on the other side of kind of the y-axis, take that function value, and then take negative that. So for the sketch, so f of x, right, oh, that's not correct. So cosine of pi over Lx, when x is equal to 0, it's going to be like that. As x goes up to L, we're going to get cosine of pi, which is negative 1. So we're going to get something like that. Okay. So that is f of x and the interval we're given. Now, if we want the odd extension, what we're going to do is say, well, okay, what is the value right here? Look on the other side. Look at the function value. Okay. Take negative that and then draw it under that. And so what we end up getting is going to be something like that. Okay. So this is the odd extension of cosine of pi x over L from 0 to L to the entire interval negative L to 0. Okay. It looks wonky because right, cosine just is not a, cosine isn't an odd function, okay, a priori. And what we're doing is we're saying, well, just take a portion of cosine and then extend it so that, right, the extension is odd. But this is what we get. Okay. Well, what about the even extension? Okay, so again, for z negative, what is the function value? Well, that's just going to be the function value, right, kind of the function reflected over. Okay. So what does that look like as a sketch? So again, cosine over here looks something like that. What is the even extension? Well, we want f of negative x to be f of x. So we're just going to reflect the sketch of this function across there. Okay. So that's the even extension of cosine defined over here to the entire interval negative L to L. Okay. Which, right, cosine is even, so cosine is its own even extension. Okay. So here's a question. So if we know that a function is even or odd, right, what can we say about its Fourier series? And so, right, something I mentioned before was, well, a Fourier series, right, we can write as a sum of an even and odd piece, okay? So we might expect that, say, if the function is even, right, well, its odd part we're not going to see. It just doesn't have an odd part, okay? And so the same will be true for a kind of the Fourier series. So if a function is even, its Fourier series will only have, right, the even piece, the cosine terms. If the function is odd, its Fourier series will only have sine terms. Okay. Yeah. Okay. So yeah. So another example, and this kind of language shows up in the book a lot. We say, compute the Fourier sine series for f of x equals 100. Okay. And in practice, we'd interpret that as, okay, well, express 100 as a sum of sine functions. Implicitly, though, there's a little more that's kind of being asked. Okay, so if we're told compute the Fourier sine series for f of x equals 100, technically, so the interpretation is, given the function f of x equals 100 on the interval 0 to L, first compute the odd extension, okay? And then once you have the odd extension, then compute its Fourier series, okay? And so now you have an odd function. Its Fourier series will only have odd pieces, which are the sine pieces. And so we will get a Fourier series of only sine terms, okay? But implicitly, right, when we say compute the Fourier sine series of something, we're really saying, here's a function on this interval, compute the odd extension, compute the Fourier series of that odd extension. Okay. So what is the odd extension? The answer is given there, but what we're doing is right, so over here, look across, take this value, look at the function value up there, take negative that, and then draw it underneath the point that we started with. Okay, so in this case, the odd extension will look something like this. Okay. And you can pick one or the other of these endpoints. In this case, it doesn't really matter. I guess for this to make sense, you need f of 0 to be 0. But, okay. So that's a sketch of the function. Okay, the odd extension of f of x equals 100. And so now what we're going to do is we're going to compute the Fourier series. So the first question is, well, what are a sub 0 and a sub n, right? The coefficients for cosine. Right, well, what we're doing is we're working with an odd function. Okay? And the observation is that if we have an odd function, we're not going to see any even pieces, right? So in the Fourier series, we're not going to see any of the cosine terms. So we would expect, and you can verify this by actually computing things, in the Fourier series, the coefficients for the cosine pieces, those are going to be both 0, or all of them will be 0. And again, this is because kind of the function that we're looking at, right? This, we took the odd extension of, and so we're working with an odd function on the integral negative L to L. Okay, but, right, we're left with the B sub n, the coefficients for sine, and so those very likely, and in this case, it's the case, those will be non-zero. Okay, so right here's a formula for these B sub n. So this is what we're going to compute next. Okay. Okay, so what does this give us? Well, our function here, f of x, it's piecewise defined. It's 100 to the right of 0. It's negative 100 to the left of 0. So B sub n, looking at this integral, we can break it up into kind of the integral from negative L to 0, and that becomes the integral of, right, minus 100 times sine, plus the integral from 0 to L, and that becomes 100 sine. And again, because f of x is negative 100 on this interval, f of x is 100 on this interval. Okay. But then what we can do is we can say, well, we're integrating from 0 to L, or negative L to 0. And so we, so in the end, this integral is going to be exactly this integral. Okay. And one way we can see that is, well, if we make the substitution x to minus x, right? Negative L goes to L, 0 goes to 0. And then the integral becomes 1 over L, integral from 0 to L, negative 100 times, so move that over there. And then move this a little back over here, times sine of n pi over L x. This is a minus in here. And then d minus x. And these bounds, these actually should be from L to 0. Okay, this minus we can pull out. It's going to cancel with that. This minus we can pull out. It's going to be a minus. But then if we want to switch the bounds of integration from 0 up to L, we're going to pick up a minus sign out here. So in the end, all the minus signs cancel. And we're left with 100 sine of n pi over Lx dx. So long story short, this we can reparameterize to get this. Otherwise, we're adding what we had before. Okay, these are the same integral, and so we're left with 2 over L times the integral from 0 to L, 100 sine of whatever. Okay. And so this formula may look familiar, right? This was the formula that we were using before when we were kind of computing and working with these Fourier series just on the interval 0 to L instead of negative L to L. But anyways, okay. And so this integral is computable. So take this 100 out, integrate this, you're going to get this expression here, evaluated between 0 and L. Right, move this out here, L and L cancel, so we have 200 over n pi. Minus cosine evaluated at L is minus cosine n pi. minus cosine evaluated at 0 is going to be 1. Okay. So the thing we end up with is going to be, well, let's see. So what is a sketch of cosine? Cosine looks like that. 0 pi. Okay. So when cosine is even, this is going to be, so when cosine is even, this is, or sorry, so when n is even, this is going to be equal to 1. So we're going to get -1 plus 1, and that's going to be 0 when n is even. When n is odd, like at pi, this is going to be -1. So -1 or -1 is +1. So we're going to get 1 plus 1, that's 2. We're going to end up with 400 over n pi when n is odd. Okay. So what do we get? Well, we were computing a Fourier series for 100. So kind of 100, and technically it shouldn't be equality. It should be the Fourier series is that. But we have equality whenever the Fourier series is continuous or the function is continuous. Okay. So we'll treat it with equality. What we're doing is we're summing over n equals 1 up to infinity for just the odd terms of, right, the coefficients we just computed times sine of whatever. Okay. So move 400 over pi, move that over there. Hundreds are going to cancel. We're going to be left with pi over 4. And then what's left over here? Well, this is going to be sum over n odd with 1 over n sine of that thing. Okay. And so again, this is still true wherever 100 is continuous. And so in particular, on the interval 0 to L, right up here. This is where we have equality. In here and in here. Okay. So let's plug in for a value where this kind of function is continuous. So we get equality and this expansion holds. So if we plug in x equals L over 2, what do we get? Well, sine of n pi over L times L over 2, that's sine of n pi over 2. There are a few cases, so it's going to be 1 when n is equal to 1, 5, 9, etc. It's going to be -1 when n is equal to 3, 7, 11, yeah, etc. And so we can see this. So if we sketch sine 2 pi, 3 pi over 2, pi over 2, 0. So when is it 1? Well, it's 1 at pi over 2. And then keep going. This will be 5 pi over 2, etc. So n is equal to 1, 5, 9, etc. And it's -1 when n is equal to 3. And then over here, 7, etc. Okay. Oh, I already had it sketched. Anyways. So what we end up with is, well, plugging all this in, so pi over 4, right? We had this expansion, we plug in L over 2. Simplify things a little bit, but then as we said, right, sine of n pi over 2, that's going to alternate between positive, negative, positive, negative, positive, negative. So we have this interesting expansion for pi over 4. Pi over 4 is equal to the sum over the odd numbers with alternating signs. Neat. So one other kind of point I want to make with this section is, oftentimes, especially numerically, we want to work with periodic functions over different intervals, right? And so this was something that kind of came up with this fast Fourier transform business, but and really kind of, right, what we started with cosine and sine when we first learned about them way back when. Sometimes we prefer the interval 0 to 2L, right? So again, we have a periodic function of period 2 pi. But other times, especially again, numerically, we'd be interested in periodic functions over intervals that aren't 0 to 2L or negative L to L. Intervals like A to B. And so kind of that's one of the homework problems to look at aspects of that. But the point I want to make is that we can still define a notion of like odd and even function. It's just they're going to be relative to kind of the center of, or like half the period of the function. Okay. So what do I mean by that? So, right, oddness and evenness, right, are relative to the center of the interval. So I can draw a picture. So 0, 2L, this is L. So for example, if we take sine, right, we say this right here is our center. Well, if we look at a point over here, right, it's going to give us some function value. If we kind of go the same distance to the other side of the center, and then look at a point here, the value that we get up here is exactly negative the value down here. Okay, so sure, sine is odd with respect to x equals 0, but in a sense, it's also odd with respect to L. Okay. So one way to kind of write down what we just said is, well, if you want to know what the value of the function is a little to the left of the center of your interval, we would think of an odd function as satisfying, right? It's going to be negative the value of the function if you go a little to the right of the center of your interval. Right. And of course, when kind of the center of your interval, this thing right here, when that's 0, you recover kind of the condition that we've seen before. But when you have an even function, right, we can say a similar thing. If you go a little to the left of the center of your interval, what is that function value? For it to be an even function, we want it to be, right, the function value if you walk the same distance to the right of the center point. Anyways.